Hi. So my name is Bill Buchanan and I lead a podcast on the world leaders in cryptography. And today I have a true world leader, Gilles Brassard. Hi, Gilles.
Hey, Bill, thanks. Nice being here.
So Gilles is a full professor at the University of Montreal for more than 45 years. He laid the foundations of quantum cryptography at a time when no one could have predicted that the quantum information revolution would usher in a multi-billion dollar industry, much less that the UN would proclaim 2025 to be the year of quantum science and technology. He is also one of the inventors of quantum teleportation, which is one of the most fundamental pillars of the theory of quantum information. In addition to this, his research focuses on areas of classical cryptography, privacy amplification, quantum entanglement, distillation, quantum pseudo-telepathy, the classic simulation of quantum entanglement, amplitude amplification, and he discovered the first lower bound on the power of quantum computers. Currently, his main interest lies in the foundations of quantum theory. In 1996, he was elected to the Royal Society of Canada. In 2002, he won the Prix Marie Victorin. Hopefully, I've got that correct.
Not too
Victorin?
bad.
Yeah, the highest scientific award of the government of Quebec. And in 2006, he was elected as a Fellow of the International Association of Cryptologic Research. In 2009, he was awarded the Gerhard Herzberg Canada Gold Medal for Science and Engineering. And in 2011, the Killam Prize in Natural Sciences, which are Canada's highest scientific honours. In 2013, he was elected as a Fellow of the Royal Society of London. He was also named as an officer of the Order of Canada in 2013 and the Ordre National du Québec in 2017. In 2018, he became the first Canadian to receive the Wolf Prize in Physics, which is considered second only to the Nobel Prize for Physics. In 2019, he received hopefully I get this right, the Mikios Quantum Prize and the BBVA Foundation Frontiers of Knowledge Award in Basic Science. In 2023, he was awarded the Breakthrough Prize in Fundamental Physics, the world's largest science prize. Furthermore, he has been granted honorary doctorates from ETH Zurich and the University of Ottawa. Wow, that's quite a career. So, what's your current role and what does a typical day involve for you?
Well, first of all, I should say that I'm half retired. I'm 70 years old now. And so I took my half retirement a few months ago, meaning that I work twice as hard, of course, but I teach half less. Um, no, seriously. These days, I've been traveling a lot around the world to give talks and participate in all sorts of workshops and conferences. Um, so my typical day does not exist. Each day is different. There's no such thing as a typical day for me. But I meet with my students. I still have three PhD students, and and I and I still teach one course per year. So I will start again teaching my Introduction to Quantum Information class in September. That's about what it looks like.
It's great. It's nice to see such a distinguished professor still teaching. I think that's
Oh
that's
yes,
really
I love teaching.
commendable. Yeah, that's
Yeah.
really great. So let's go right back to
You
your
say it's
school
commendable.
days.
It's commendable if it were punishment. It's you
Yeah,
take it as a
that's
reward.
right. Yeah, that's
That's how you get.
very
That's
much.
how you stay young.
Yeah, that's very much a great thing. So, what were your days at school like? What were you like as a pupil in your early days?
Well, school was the best part of my life. When I was a child, I that's where I escaped from reality, and I know that some other people think that school is a prison. Not for me. For me, it was heaven. I went to a private school. Well, I know that in England, a private school is what we call a public school here, and vice versa. But so I'm not sure if it's clear what I mean by a private school, but privately owned school for my most of my undergrad, most of my studies before the university, and it was very good environment for me, very pleasant. I never understood when people who would say that oh no, it's Monday, I can't wait for Friday. It was always the opposite for me.
And what sparked your interest in maths and physics?
Well, it was one of my older brothers, not my oldest, but one called Robert, who was about 7 years older than me, and he taught me college level mathematics when I was in primary school. When I was less than 10, I knew some of this mathematics, so-called higher mathematics, and how that was such an amazingly good at teaching that it was impossible not to love the topic. So I said my best memories of my childhood were going to school. That's not true. It were probably else teaching me mathematics. And then in 11th grade, which means the last year before university, I had a math teacher called Raymond Zacour, who was amazing. Well, the second best teacher I had in my life, Robert being the best. And he really gave me a rigor and the importance of well, this is what he gave me a curse, which is to be a perfectionist.
Perfectionist, yeah, excellent. And what got you into cryptography?
Yes. Oh, after my bachelor's degree at the university, which I did in Montreal, I decided to go to PhD. No, I also had a master's in Montreal, and then to go for the PhD abroad. And this was maybe the best advice was ever given to me by my master's advisor, who essentially kicked me out of my cozy nest, and didn't force me, but made me understand the importance to go somewhere else. So very reluctantly, I left home and went abroad to get a PhD, specifically at Cornell University in Ithaca, New York. That was at a time when it was okay for a Canadian to go to the United States. Of course, it's not anymore, unfortunately. Maybe it will come back at some point. So, anyways, back to my PhD. There, I had the advisor that agreed to supervise me, who won the Turing Award later, was John Hopcroft, a totally amazing person, very inspiring. And so he agreed to be my supervisor and essentially left me free to do work on whatever I would want to, which is also what I've done to all of my students afterwards. I believe the best way to get the best of someone, you have to leave him free to think, free to choose what's interesting. In any case, so Hopcroft, well, despite what I said, Hopcroft at some point gave me a problem I might want to work on. And that problem is still unsolved today. This was in the mid-1970s. So that problem is still unsolved today. But while working on it, I realized that if I had some mathematical object, that would help me make progress on the question. Not solve it, but make progress. So I went to Hopcroft and asked him, have you ever heard of this thing? And he said, oh, yes. It's just been out in a paper published in 1976 called New Directions in Cryptography by Whitfield Diffie and Morton Hellman. Yeah. So Hopcroft was not by any means a cryptographer, but he'd seen that paper. Indeed, that's the most important paper of the second half of the 20th century in cryptography.
Yeah.
There's a paper that gave birth to public cryptography and digital signatures and all that stuff. And yes, that paper included something that was very much like what I needed to solve Hopcroft's problem, which was no longer of any interest to me because I fell in love with cryptography when I read that paper, and I changed completely my topic of interest towards cryptography, reading New Directions. Really an amazing paper. Well, and I should say that I already had previous interest in cryptography as an amateur, having read books like The Code Breakers by David Kahn, but I never thought I would work on it as a professional life until I read New Directions, and then from there I reoriented my PhD studies. My thesis in the end was about public cryptography, which was a very, very new topic at the time. So that's all. It all started there.
Yeah, that's amazing. Yeah, it really is a truly fantastic paper. And I have actually interviewed Marty Hellman and Whitfield Diffie, and they're two very different people.
Very different.
Marty came up with the discrete log method, and Whitfield was very much about this, as you say, future directions, about public key encryption. I also met with Ralph Merkel, who also came up, and I think you've done some work on Merkel puzzles that we can come back to later. So, what's your...
Let me jump on this. When I said that Whitfield Diffie and Martin Hellman introduced... Oh, by the way, I realized only recently that I've known all along that Diffie was Hellman's student. But only recently did I realize that Hellman is younger than Diffie by 1 year.
Right. Yeah.
Anyways, what I wanted to add is that, yes, I just said that they introduced public cryptography and digital signature. And it is absolutely true for digital signature. But public cryptography had been invented by Ralph Merkel 2 years before. And the difference is that whereas Diffie was lucky enough to have an advisor, an enlightened advisor, Hellman, who understood the idea and the importance of it and encouraged him, and then they worked together and wrote this 1976 paper. Merkel had this idea while he was taking a course at Berkeley. Diffie and Hellman were at Stanford, Merkel at Berkeley, that's next door. And Merkel had these ideas very much like Diffie and Hellman's 2 years before. While he was taking a course on computer security, I think, and the professor asked all the students to propose a couple topics for a research subject for the course, and Merkel proposed Merkel proposed what really is now known as public key distribution, and somewhat more so public key establishment. And the professor did not understand, and Merkel just dropped the course. He dropped the course, and it's a tragedy. But then he kept working on it, and he got it published 2 years after Diffie Hellman. That's life.
That's right.
But anyway, since I'm in the history, the person who really invented the idea that two people could communicate in secret, even if they don't have a prior secret, was neither Merkel nor Diffie and Hellman. It was John Ellis in 1960, working for the British Secret Services. He had the idea that it might be possible, had no clue how to do it. And he pitched the idea around, and it was finally discovered by Clifford Cox. In 1973, Clifford Cox invented something very much like RSA. But of course, they kept it secret because it was in Secret Services. All right, end of history. Go on.
Yeah, it's an amazing story. And
by the way, sorry to interrupt that, but if you have not interviewed him yet, I think Cliff Cox would be interesting.
Yeah.
He might not be as willing to talk as I am because he worked for the Secret Services, but still.
Yeah. I think it took a while for the UK to award them with honours, and it was a real shame that they didn't get awarded
Yes.
the prizes at the time. But I suppose that's the thing with
Well, at least he was elected as a fellow of the Royal Society.
yeah,
Uh,
yeah, that's amazing.
but what I think what is more sad is that the British government finally decided to lift the secret
Mm,
on these amazing discoveries of their secret services 1 month after John Ellis's death.
mm. That's
That is
sad.
more of a tragedy. At least Cox
Yeah,
had a chance to say, yes, it was me.
yeah, yeah. That's sad. And so, what's your favorite area of quantum computing? You work in so
I,
many different areas, and as I said, you got into the area really when it wasn't a big topic. I
correct.
mean, why did you get into it, and what's your favorite area that you work on?
Well, indeed, I started on this topic even before quantum computing was invented. Um, so let me start by changing your question, which was your question was about my favorite topic in quantum computing. There is a misconception that quantum computing is equivalent is to quantum information science, but it's not. The big topic, the general topic, is called quantum information science and or quantum informatics. And quantum computing is one of the interesting, but only one of the subtopics of quantum information. So I got involved in quantum information science as early as 1979, which is uh, before Feynman thought of quantum computing in 1981. So back to your question, what's my favorite topic? Not in quantum computing, but in quantum information. It's first of all the thread of what really makes me interested is when one can use quantum theory or quantum information to achieve tasks that are strictly impossible in the classical world. And quantum computing is not one of them, in the sense that quantum computers, yes, whenever we have them, they will be able to compute things that would take billions of years for a classical computer. That's true. But it will not be able to compute anything that a classical computer cannot compute in principle, given unlimited time uh, or unrestricted time. In other words, the notion of what is computable, which was formalized by Alan Turing, one of the greatest mathematicians of all time, for whom I have complete, total admiration. So Turing formalized the notion of what is computable, and quantum computers don't change that. So when I said that what really makes me interested are things that quantum theory makes possible, at least in principle, sometimes in theory, sometimes in practice, and that would not be possible with the classical computer. Uh, there are things, and quantum cryptography, we talk about it later, is one of them. Quantum cryptography uh, does something which Claude Shannon proved to be impossible because he didn't think of quantum. Now, quantum computing, of course, is interesting. I'm not saying the opposite. It's very promising, and I contributed to some of it, but it's not what makes me most interested.
Yeah, yeah, and obviously Moore's law has shown us that we have increased computing power over the years, but really we've probably hit the limit as to how far we can go with silicon. Do you think quantum methods is the natural succession to silicon?
I would not say it that way. Um, Moore's law indeed has been holding strong for much, much longer than Moore probably had expected. But
Yeah.
and Moore's law indeed hits a wall when the Moore's law says that uh, computing elements uh, will get half the size and twice the speed every roughly 18 months.
Mm.
But that's exponential. which means that at some point, if really components like transistors, if really they become half the size every 18 months, at some point it would be smaller than an atom, and at some point smaller than an electron, and at some point it just doesn't make sense anymore. So Moore's law, as stated, cannot hold forever. And the enemy of Moore's law, in a sense, is quantum, because if the world were infinitely divisible, then why couldn't you continue making things half as small? So the quantum world is what makes Moore's law impossible to sustain. But we're always better off playing along with nature instead of trying to fight it. And nature gives us a block to quantum, to Moore's law, but gives us something else, which is much more amazing, namely quantum computing. Now, where I would not agree with your statement is that it's not a continuation of Moore's law. It's totally different.
Yeah.
And in particular, in most people who don't really know what they're talking about when they talk about quantum computers will say, oh, it goes much, much, much faster than a classical computer, like 1,000 times, 1,000,000,000 times, or 100,000 billion times faster. No, the quantum computers work on different principles. They don't go so much faster than classical computers. It depends what they want to do. For some tasks, they would be faster. So some tasks, they might even be exponentially faster. For some tasks, they would be just quadratically faster. But it's not faster by a constant factor. It's not so many times faster. So Moore's law is nothing to do here. And I like the following image. Think of a labyrinth. You're trapped in a labyrinth and trying to escape from a minotaur. And you try to find your way out in this two-dimensional system. And you hit walls and turn around and try to find your way. And it's very difficult. If instead you could just fly out using a different dimension. So by using a third dimension here, you fly out of the labyrinth, and then there are two different things you can do once you do that. One is to look down at the labyrinth, and now that you see what it's like, you can, in your mind, decide on what's the best path out. Then you go back down and take the optimal path and get out. And at the same time, maybe you can spot the minotaur, know where not to go. Or you can even do better, and since you're flown out, well, why not just go away? Get out of the labyrinth from the third dimension. But it's only an image, but quantum computing is a bit like this, where instead of doing it the old way, you move to a different dimension. Now, it's a different dimension in what's called a Hilbert space. It's not a third or the fourth dimension. It's not in our physical space. So that's why it's only an image. But really, by using different dimensions for computing, then you can do things differently. It's not always faster, but it's different. And sometimes it may be very, very much faster.
And obviously with Shor's algorithm and Grosvenor's, then that is one problem that quantum computers have solved. Can you just give a quick outline of how Shor's algorithm and Grover's algorithm are a risk to the methods that we talked about earlier, the traditional public key encryption methods, elliptic curves, discrete logs, and RSA? Very good.
So let me tell you about the importance of these algorithms as opposed to how they work. I may try to say something about how they work afterwards, but let me first talk about the importance, why it's relevant, why it's very, very much relevant to our society. So before I mentioned these public key cryptography ideas of Diffie, Hellman, Merkle, Cox. These have been implemented on a very large scale, in particular in attempts to secure the internet, all communications on the internet, and transactions of all sorts. So when you go on the internet and you open a browser and you type HTTPS for secure, and you see a little padlock appear in your browser, this is meant to tell you that your communication is secured. but it's not. It's not at all, and it's really, really very bad. Let me be more precise. It's been used for more than 40 years now, and everybody uses it. It's used maybe a billion times per day on Earth, probably more than that. Every single day, people rely on that. But these cryptographic systems, as we call them, this cryptographic infrastructure, it's based on a belief that some problems are computationally very hard, so hard that it would take the lifetime of the universe to solve. One of these problems is factoring. If you're given two big numbers, when I say big, I mean 1,000-digit numbers, you're giving two very big numbers, well, multiplying them is a joke. It's very easy on a computer. You can do that in a fraction of a second, less than that, even if they're very big. But once you're given the product, to break it down in its two factors is something that we believe is infeasible, not impossible, but infeasible in the sense it might take more than a lifetime of the universe. And this was at the basis of the famous RSA, as in Rivest Shimmy Edelman crypto system proposed in 1978, I think. And they were so confident that these three inventors, for whom I have great respect, but they were so confident that they wrote an article in the Scientific American in 1979, I think, I'm not sure.
Martin Gardner, yeah.
And in fact, the RSA crypto system was published as a technical report and was distributed by mail, physical mail at the time. But it really became hot, I would say, because it was published in Scientific American. And in that article, they proposed a challenge their readers. Here is a secret message, which we encoded with our system that we just described. And here's the public key. Now, anyone who would be able to find the plain text would be awarded $100. Not much, of course, but they were poor academics. I mean, in those days, they were not as rich as today. And but what happened is that, and they felt very confident because using the most efficient algorithms for factoring numbers known at the time, and taking account of Moore's law, and thinking we have a computer that would be 1,000 times faster soon, it would still take the lifetime of the universe. So they felt very safe. In the end, it was broken after less than 20 years. I forgot how many exactly. It was broken by two different ways. First is that a better algorithm was discovered, which still took exponential time, but significantly better than the best that was known when RSA gave the challenge. Indeed, the computers were going 1,000 times faster. But the other thing that they did not foresee was the internet. Specifically, that there was an effort, a world effort, just for the sake of it, just for the fun of it, to rise up the challenge and break this crypto system, not a crypto system, but break this particular ciphertext. And thousands of people chipped in with their personal computers. It was all distributed. So the new algorithm could be implemented in a distributed fashion. So you had thousands of people around the world who were giving all their idle time on their computers to crack the problem, all communicating over the internet to send their partial results to a central place. And then when enough data was collected by all these people, then a supercomputer at the time was able to munch on it and finally find the answer. And then the $100 was given to the Electronic Frontier Foundation, I think.
Yeah.
Anyways, so what's important here is that when you think that these systems are secure, it could always be that more efficient, better algorithms are found, or better ways to implement them. And we still don't know if the current key size used for RSA encryptions could be broken by a classical computer, because we don't yet have, and well, nobody has claimed to have a classical algorithm that can break that. But we've known since 1994 that a quantum computer could, and that's Shor's algorithm. So Peter Shor, and independently in the Soviet Union, Alexei Kitaev, discovered that a quantum computer would be able to factor big numbers very efficiently, if only we had one. I mean, a quantum computer. And in those days, it sounded like it was science fiction. Quantum computers sounded like, well, it's a very nice theoretical idea, but this will never be built. 1994. And people continue to use the old techniques for decades, even though the red flag was there. And then as decades passed, it became more and more obvious that quantum computers will be built. We have small scale versions already that are working, but a big enough quantum computer to implement Shor's algorithm and break RSA and also Diffie-Hellman, because Shor also discovered how to break Diffie-Hellman. That is coming. I'm not asking in how many years, but there's no doubt that it's coming. There's no block anymore. We know how to do it. So it's a matter of time. Now, what this means, the obvious thing it means, is that if we continue to use these cryptographic techniques, once there's a quantum computer, there will be no secrecy anymore. So you might be tempted to think, if I have a quantum computer today, my data is gone tomorrow. But that's wrong. The real worry is that if I have a quantum computer tomorrow, my data is gone today. And the reason is that even if we believe, which we don't have a proof of, but even if we're willing to believe that this cryptographic infrastructure that's been used for decades resists all possible reasonable time attacks by a classical computer, if we believe that, that does not prevent people from collecting encrypted data as it goes through the internet and just storing it, waiting. And on the day a quantum computer becomes available, all this data can be taken out of storage and decrypted retroactively. In other words, as soon as a quantum computer big enough becomes available, the entire internet, everything that has, or almost, there are a few exceptions, but almost everything that's been sent over the internet, all transactions, everything that was sent under the cover of this little padlock will become an open book. That's what we call the harvest now and decrypt later paradigm. And nothing can be done to save it. This data in encrypted form is already in the hands of the opponent, whoever is the opponent. And you can't take it out. You can't take it from them. So that the past is lost in a way that it cannot be retrieved. There's no way to save the past. All we can hope for is save the future by using better techniques. So that's the importance of Shor's algorithm. This is because there's one for factoring, one for discrete lock. And I mentioned before that before Diffie-Hellman, Merkle also had an idea how to do how to do public key establishment, which is a technique by which two people who have no secret initially can have a conversation. And at the end of it, they can distill a key that is the same for both of them in secret to someone who listened to the conversation. So Merkle was the first who, in the academic world, to propose a method to do that. And his method is broken by the other best known quantum algorithm, namely Grover's algorithm. So Grover's algorithm and Shor's algorithm, the two most important quantum algorithms so far, break both Diffie-Hellman and Merkle. and that's a disaster.
Yeah.
What's even more of a disaster is that at about the same time in the late 1970s, when RSA came along and Diffie-Hellman, there was also Michaelis. Michaelis also proposed a different way to do key establishment, classical, of course. And as it stands today, nobody knows how to break his approach with a quantum computer. And in those days, we could have used that as a standard. But instead, we, meaning the society, we latched onto RSA and Diffie-Hellman. If in those days instead we had used Michaelis, perhaps we would not be in such big trouble today. Or perhaps if it had been used in real life, that's the one that would have broken. Who knows?
Yeah. It's quite slow for the key generation. I think NIST have obviously approved Kyber, which is a lattice method where the security isn't quite proven yet with learning with errors. But the HQC is obviously an alternative with an error correcting code. So maybe Macalis's method will live on. I think it will get standardized eventually. As you say, it's been around for a long time. Unfortunately, he departed from the earth a few years ago.
I was not saying that Michaelis is the best solution today.
Mm-hmm. Yeah.
And I understand why it was not used, why RSA and Diffie-Hellman were preferred in those days. I understand all that. What I'm saying is that in those days, we knew a method that we don't yet know how to break with a quantum computer. And when you said that there was some other method that NIST has been studying, and you said that it's not quite proven yet that they're secure. I'm sorry. It's not proven at all. And that's the main weakness. There are two main weaknesses to classical public key cryptography. One is that we have no way, no technique, no mathematical techniques whatsoever have been developed to even start to try to prove security for these methods. It's all built on sand completely. There's nothing. There's no theory that has any mathematical value to make us believe that these are hard to break on a classical computer or a quantum computer, but either way. So it all lies on belief that something is hard when we don't know how to prove it. So that's one of the two main weaknesses of classical cryptography. I'm talking about public key. The other is the one I already mentioned, which is the susceptibility to harvest now and decrypt later attacks. So even if indeed today nobody knows how to break it, well, maybe tomorrow they will. And if they've stored the encrypted message, they can decrypt it later. And that's why we need something else.
Yeah. But obviously, hashing methods are fairly secure, and the Merkle tree is used in the Sphinx Plus signature methods. So hopefully, the hashing methods will be much more robust than some of the other methods, because obviously with signatures we see dilithium. And also Falcon, which are two lattice methods. Again, there will be weaknesses there, but the Merkle tree approach does seem to be fairly secure.
It seems to be, yes. It seems to be. It might be.
Great. So could you go through just a quick history of quantum computing? What was the main generations? What were the big advancements that happened in quantum computing?
All right. I hope you'll allow me to answer your question about quantum information science.
Yeah.
Because quantum computing was not at the start of it.
Yeah.
So quantum information science started in 1968 with Stephen Wiesner. Stephen Wiesner was doing his PhD at Columbia. And he was the first person, as far as I can tell, who ever thought that it would be possible to use something quantum to achieve a task having to do with information processing, a task for which we could prove that it's impossible classically. So exactly what I said at the beginning, I find interesting. So Wiesner wrote a paper that he called Conjugate Coding in 1968, in which he gave two examples of what he called novel forms of coding made possible by Heisenberg's uncertainty principle. And the two ideas he had in that first paper, the best known of the two is quantum money. Mm-hmm. And it's totally impractical. Mm-hmm. But it's a crazy idea, which was at the start of everything. So the big lesson here to be learned that crazy ideas can be very fruitful. I'm not saying that was the first time in history it happened. So what Wiesner thought of was that given that quantum information cannot be measured without being disturbed by Heisenberg principle, and that it cannot be copied. This is known as the no-cloning theorem, which was discovered later, after Wiesner's work. But still, Wiesner had this idea, this intuition, that quantum information could not be copied. And so given that, the idea of quantum money, quantum banknotes, is obvious. If you put quantum information on a banknote, then it cannot be copied. That's it. As simple as that. Now, it's impractical because in those days, at least, to keep quantum information alive was not possible, technologically speaking. But in theory, there was no obstacle. If it were just that, it would be impractical, yes, but also useless, because if it's very nice that nobody can copy a quantum banknote, but if you cannot verify its validity, what's the point? Anybody could make another one that looks just like a real one, but how could you tell one is good, one is not good? So you also need a way to check validity of the quantum banknote. And Wiesner had a solution for that as well. But in Wiesner's original paper, in order to check the validity, you needed to have the same secret that was used to create it. So that a bank or a mint could make banknotes. They would be unforgeable by quantum theory. But nobody could check validity except the bank who made it. So that it still is useless. You could not spend it anywhere because the merchant would not be able to test. All you could do with it is go to your bank, you withdraw a banknote from your bank account, whatever you need. Take the banknote, physical banknote, say thank you. Then you cannot spend it anywhere because nobody can verify it's valid. All you could do is run around town and come back to the bank and deposit it back because they could check validity. And you better do that. You better do that within 1 millisecond. So how could anything be more useless? And yet, it was the start of everything, as I said. In the same paper, Wiesner proposed also what is known today as oblivious transfer, which he called multiplexing channel, which is a way by which one could have two classical messages, encode the two messages into one quantum signal and send it to a receiver. And then let the receiver decide which of the two messages he reads. And the receiver can choose to read one or the other of the two messages, but cannot read both. And the sender cannot tell which of the two messages was chosen by the receiver. Again, this was invented 15 years later in cryptography under the name of oblivious transfer by computer scientists who had no idea that Wiesner had invented before. Now, oblivious transfer cannot be, we know today that oblivious transfer, quantum oblivious transfer, cannot be unconditionally secure. That's something else. But still, the idea was there in Wiesner's paper. And he even proved in his own paper that his scheme was not unconditionally secure. So 1968, Wiesner. So that's the beginning of quantum information science. And then Wiesner submitted his paper. And he wrote the paper as a physicist. And he's a physicist. He passed away a few years ago. Being a physicist, he wrote it in physics jargon, and that's okay. But then he submitted to an engineer's journal, namely IEEE transactions and information theory. And of course, neither the editor nor any of the referees could understand any of it. It was rejected. Rightly so, I would say. And what could he have done? He could have, I think the most obvious thing he should have done is resubmit to physics journal. Why did I will never understand why he didn't do that in the first place. Or he could rewrite it in terms that are comprehensible by computer scientists and resubmit the same place. I don't know if he could have done that. I mean, I know he had the knowledge to write as a computer scientist, but he didn't either. What he did was put the paper in a drawer and moved on to something else. And that could have been the end of the story. Fortunately, Wiesner had a good friend, Charlie Bennett. They had gone to undergraduate studies together, but now they were doing their PhDs in different places. But they visited each other at times. In 1970, Wiesner visited Bennett and told him about his ideas. And Bennett took out a sheet of paper and started writing notes, taking notes of what Wiesner was telling him. At the top of the page, he wrote, quantum information theory. Wiesner's told me that, blah, 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 blah. So Bennett understood how important it was and made sure that it would stay alive. And he kept talking about it around him and met with complete lack of interest by everyone. Nobody showed any interest in listening to Bennett's talking about Wiesner's ideas. Possibly because he was talking to physicists all the time. He's a physicist. Well, PhD in chemistry, but he's a physicist. Until 9 years later, in 1979, he met me. And the difference is that I am a computer scientist, moreover trained in cryptography. And I was fascinated. And we took it from there to invent quantum cryptography, which really is based on Wiesner's ideas initially. And just to make the story more interesting, I was swimming at a beach in San Juan, Puerto Rico, minding my own business, having never seen this Bennett, when he swims up to me and starts telling me. So the first time that Bennett told me about Wiesner's idea about quantum anything was in the ocean. He just told me, hey, I have a friend who has found a way to use quantum theory to make unforgeable banknotes. It's not something you expect when you're swimming. And I don't know, I like to say, it's probably not true, but I like to say that if I had been on firm ground, I would have run for my life. But in the ocean, what could I do? I had to listen politely. And so Bennett told me about Wiesner's ideas, and I realized what I told you just before, which is how useless it was, because it could only be checked by the people who actually made the banknote. It was useless. But at the same time, I had just finished my PhD on public cryptography. And I immediately saw that public cryptography could be used. That we could think of having a secret key that would be needed to make the banknote, but a public key could be used to verify it. And all of a sudden, it became just as impractical as before, but it became no longer useless. And that was our first paper, which we published in 1982, because we didn't take that seriously either. And from there, Bennett and I developed quantum cryptography. But the first paper, whose title was Quantum Cryptography, at the Crypto 82 conference in Santa Barbara, California. Well, that first paper was about quantum banknotes that we recalled quantum subway tokens. But the title was there, Quantum Cryptography, already in 82. So this is how quantum cryptography took off. From there, we invented BB84. We'll talk about it later. In parallel, Feynman in 1981, so after this original work with Bennett, uh, but independently, in parallel, Feynman invented the idea of quantum computing. A talk at the Endicott House, MIT Endicott House in 1981, a talk at which Bennett was, but I was not, unfortunately, in which Feynman asked the question, can we simulate physics with computers? And of course, in those days, he meant with a classical computer. And he gave all sorts of reasons for which the answer is probably no. That because of quantum theory. If you want to simulate physics, you need to be able to simulate quantum physics in particular. And quantum physics has so many parameters that you would need exponential slowdown on a classical computer to simulate quantum physics. And it's true that if you simulate quantum physics on a classical computers by the obvious method, then you need an exponential slowdown. It is still unknown if there could be more efficient ways on classical computers to simulate quantum physics. We don't know that. But Feynman gave arguments that probably not. And then he had a flipping sentence, a paragraph. Oh, if we had a quantum computer, maybe that would be different. So he thought of quantum computers as a way to simulate physics, quantum physics, efficiently. That's why he invented the quantum computing. But in his original 1981 paper, or talk, I would actually talk, it was just a flipping remark. And then he came back shortly afterwards with a fully fledged idea of how quantum computers, what it could be and what it could do. But in his mind, what it could do still was simulate physics. Then we had to wait for David Deutsch. David Deutsch, 1984, I think, maybe 5, I'm not sure. David Deutsch was the first person to think that a quantum computer, he knew about Feynman's idea, but he realized that if we could build a quantum computer, maybe it could be used to solve problems of interest to computer scientists or mathematicians, not only to physicists, even though Deutsch himself is a physicist. And he proposed the first problem for which quantum computers would have a very, very slight advantage over classical computers. So that was 84, 85. And then the question remained open for several years. Could quantum computers give a significant advantage? And could he do so for a practical problem? And to this last question, the answer was yes by Shor's algorithm. Although it's an important remark that we still don't know how to prove that Shor's algorithm goes faster than anything possible classically. It is possible that we can factor big numbers efficiently in a classical computer. We just don't know. So all we can say is that Shor's algorithm goes exponentially faster than the best method currently known on a classical computer to solve the same problem. So that's how quantum computing started. At that time, as I said, it seemed like quantum computing would be it's just a nice theoretical idea, very crazy, could never be built. In particular, could not be built because of how fragile quantum states are. And it seemed that in these early days, early 1980s, and that because quantum states are so fragile, one would never be able to build a quantum computer that would run long enough to do something useful, like implementing Shor's algorithm. And then the same Peter Shor came up with the idea of quantum error correction. So Shor, until then, it was believed that error correction, which is used routinely on classical computers or classical communication, would have no analog in the quantum world. And the reason is that in classical information processing, the way you do error correction is by redundancy. You take the message you want to transmit or store, and you add redundancy, and then you send a redundant message or store it. So when you recover it, if the redundancy doesn't quite match, then you can figure out if there's not too many errors. You can figure out what's wrong and fix it. The most obvious error correction code is you send a single bit, you send it 3 times. So as long as only one bit is received incorrectly, the majority of the 3 bits is still correct. Mm. So the most primitive error correction code, classical error correction code, uses copying. You copy the information 3 times in this case. And that's exactly what the quantum no cloning theorem tells us we cannot do. So it was believed that because quantum information cannot be copied, there would be no such thing as quantum error correction. And as long as there would not be quantum error correction, the hope to build a quantum computer that would work long enough to do something useful was very small. Not impossible, but not very likely. And then the same Peter Shor discovered, as I said, how to do quantum error correction. And that changes everything. Personally, I would think that Shor's invention of quantum error correction is far more important than his invention of the factoring algorithm. But when you put them together, that's what made quantum computing take off. And before those ideas of Shor, quantum computing was not very popular. It was studied by a few freaks like me. And after Shor's algorithm and error correction, it took off. And thousands of people decided to work on quantum computing. So that's really the early history of first quantum information and then quantum computing.
It's really interesting. I talked to Victor S. Miller. Victor S. Miller was the co-inventor of elliptic curve cryptography along with Neil Koblitz.
Yeah,
and I think, I may be wrong, but the Crypto 82 conference, he presented elliptic curve cryptography there. Maybe 83 or 82, but I'm fairly sure it was around that time and nobody took it seriously at the time.
Oh, I didn't know until Van Stone decided.
And Van Stone, the ECDSA, and obviously Satoshi Nakamoto, and elliptic curve took a while to take off. And I think even Ron Rivest wasn't really that keen on it at the time, but it did.
Well, it was competition.
Yeah, so I'm fairly sure it was Crypto 82. I have a lovely photograph.
I'm not sure. I was at almost all the early cryptos except 83.
83, yeah.
I was not at Crypto 83. I heard of Victor Miller's and Neil Koblitz's elliptic curve ideas at the beginning, shortly after it came out. And it sounded really interesting to me. But Shor's algorithm breaks that as well.
Yeah, that's exactly the discrete logarithm.
RSA, Diffie-Hellman, and elliptic curves. All of that, every single thing that's been used on the internet for decades to so-called protect security vanishes when you have a quantum computer.
Yeah. So you mentioned the BB-8.4 protocol, which I think you invented. Could you just outline what it is and how it's applied in practice?
Sure. So back to the story, my story with Charlie Bennett. After we published at Crypto 82 this first quantum cryptography paper on quantum subway tokens, which really were banknotes, and which was not, it was cryptography because we were using public key cryptography ideas to turn Wiesner's useless banknotes into useful banknotes. But I would not say it was really mainstream cryptography. So at the time, we realized that, well, this was fun, but was not something on which we worked seriously. It was not our day job, neither Bennett nor me. It was just, let's get together and talk some more about these crazy ideas, which we never thought would take off in the real life. But at some point, I'm not sure who between Charlie and me realized that the main impractical aspect of these quantum banknotes is that they ask to keep quantum information alive in a single place, namely on the banknote. And the most obvious form of quantum information that we had at the time was photon polarization. And keeping photons still in one place is not so easy. It's not technologically very reasonable, especially not in those days. And then at some point we had this aha moment that, well, photons are meant not to stay in place, but to travel. They are meant to communicate. And all of a sudden we realized that we should use Wiesner's ideas not for these banknotes, but for communication. And being a cryptographer by training, it was natural for me to think of, oh, let's use quantum information to do cryptography. Want to communicate, so why not communicate in secrets? It was a most natural thing for me to think about. Now, I must add that in those days, we knew that Wiesner's second idea, he had this banknote. He also had this multiplexing channel, WS transfer. I mentioned that. And in Wiesner's multiplexing channel, he used photons to transmit information. So we did not invent, Charlie and I, the idea of using quantum information to transmit information. It was all in Wiesner's paper, but somehow we hadn't realized that in those days. It's very strange. Anyways, what happened is that as soon as we decided that quantum information should be used for cryptographic purposes, then we invented the first method in which we encoded the information that we wanted to transmit secretly. We encoded the information in the quantum signal, much like Wiesner had done with his multiplexing channel, but although in a different way. And in our initial idea, Alice and Bob would both need to have a secret key. And let me take a small break to say something technical about quantum information. So about photon polarization in particular. So a photon can be polarized at any angle. And if you know ahead of time that a photon is polarized either horizontally or vertically, then in principle you can tell which it is with arbitrary precision. Same thing if you know ahead of time that it's either plus or minus 45 degrees polarization. Then you can distinguish them with arbitrary precision. But if you're told it's one of the four, but not told which one, then no measurement can tell you with certainty or with enough precision which of the four it is. So our first idea for quantum cryptography, not a banknote, but for transmission of secret information, our first idea was that if Alice and Bob share a secret key, as long as the message they want to transmit, much like the one-time pad, but that key tells Alice for each bit of the message to be transmitted, whether to encode this bit with what we call a rectilinear polarization, in which this would be a 1 and this would be a 0, or a diagonal polarization where this would be a 1 and this would be 0. So if we sorry. So Alice would send one polarized photon per bit of message, encoding it at random, either like this or like that, in terms of polarizations. It would send these photons to Bob. And if Bob had a copy of the key, then Bob would know which measurements to make on each photon to recover the bit. But an eavesdropper would not be able, because for an eavesdropper, all four possibilities are there, and no measurement can tell the eavesdropper which one is good. So an eavesdropper would have a limited amount of information that can be obtained from the transmission, and moreover, any attempt by the eavesdropper would create a disturbance that the legitimate receiver would detect. If it were only that, then the eavesdropper would be able to get partial information. That's no good. So we added one level of classical one-time pad. So at the end of the day, Alice and Bob needed a key twice as long as the message. First, there's a classical one-time pad, then a quantum one-time pad. That's sent to Bob, who can decipher because he has the same key. And now any attempt at eavesdropping would be detected, but would not give any information on a message because of the first classical one-time pad. So that an eavesdropper would not gain any information on the message, but his presence would be detected. And the whole point of this is that the one-time pad, I've been talking about it without saying what it is, I'm sorry. But the one-time pad is a classical technique that was invented in the 19th century. The one-time pad is provably secure. Was proven by Shannon in 1949, I think. The one-time pad is provably secure, unconditionally secure for the transmission of classical information, but it requires a key. It requires a key as long as the message. And moreover, this key should be used only once, hence the name one-time pad. So it sounds impractical, but it was used, for instance, on the red telephone during the Cold War between Khrushchev and Kennedy. In any case, what Shannon proved is the one-time pad is unconditionally secure under three conditions. That the key is purely random, known to the two legitimate receiver participants, of course, and completely unknown to the eavesdropper. And what Shannon proved is that if these conditions are met, then an eavesdropper who would intercept the coded message, the ciphertext, would gain no information on the clear text. However, he would gain information on the key. And that's why you should never use the same key twice. Because if you use the same key a second time, then the condition that is unknown to the eavesdropper is no longer met. And that's why it's broken. All this to say that this quantum idea that I had with Charlie, it was in 1983, this quantum idea, if the eavesdropper, if we don't detect eavesdropping, and again, any attempt at eavesdropping leaves a trace that we can detect. If we don't detect eavesdropping, then the key can be reused. See, the reason you should never use a one-time pad, classical one-time pad twice, is that if the eavesdropper has access to ciphertext, he gets information in the key. But then we couldn't know if the eavesdropper has had access to ciphertext. Because if he has, it left a trace. In which case we just scrap the key. But if there's no eavesdropping and we detect there's no eavesdropping, then we can reuse this key indefinitely. So we call that a reusable one-time pad. That was our first idea, 1983, which we submitted to, maybe it was 82, I'm not sure. But we submitted to a major computer science conference. And it was rejected. And then we did not do like Wisner. It was rejected. Actually, we sort of dropped the idea, just like Wisner, because in the meantime, we come to a better idea, known as BB84 today. The main defect of what I just described to you is that it's very susceptible to a loss on the channel. In real life, when you send photons on a single, because we're talking about sending single photons here, single photons on an optical fiber, unless the fiber is very short, most photons won't get there. So you should expect maybe you get 1% of your signal. So if we use the technique I just said, and you get at the end 1% of the message, there's no eavesdropping, but the channel is imperfect in terms of loss. So at the end, Bob receives 1% of the message that Alice wants to send. That's not very useful. And that's when we had the second aha moment, which was, let's use this technique not to send an actual message, but to establish a key, a random key. And now, if only 1% of the key is obtained, it's shorter, but it's still random, it's still secret, and life is beautiful. So the idea is that to deal with loss on the quantum channel, let's forget about sending a message. Let's just establish a key. And if we're able to establish a key, as long as the message we want to send, only once the key is established will the actual message be taken out and coded as with a one-time pad with that key and sent to Bob. So that now there is no risk of losing, the confidentiality is assured because the message stays at the sending place until a secure key has been established. And only then is it sent to the other party and coded with a one-time pad. And that's how we get unconditional security with BB84. And the way that we invented it again does not need a previous key between Alice and Bob. So Alice and Bob have no previous key initially, and they establish a secret key. That's what BB84 is about. And that secret key is used as a one-time pad, ideally, to send the actual message. So that's what we invented. In fact, BB84 was invented in 1983, but published in 1984. And that too is funny because, as I said, our ideas, just like Wisner's, had been rejected, except for the Crypto-82 subway tokens. And at the time, 84, I had this colleague in Montreal, in a different university, but still, whom I knew, an Indian guy called Vijay Bhagava, who became very prominent at the IEEE. Later on, he almost became president of the IEEE. But Vijay was in charge of a special session on coding and cryptography at a conference that was organized in Bangalore, India. And he told me, hey, if you want to visit India, submit something to my conference, and it's accepted already. So the funny thing is the BB84 was, of course, I sent BB84. So the funny thing is BB84 was finally published because it was never submitted. it was accepted in a somewhat, I would not say unethical, but unusual way. That's how BB84 took off. And in those days, we did not take ourselves seriously, and neither did anybody else. But as the years passed, we decided that maybe it was more serious than we had thought initially. And we built the first prototype in 1989. And that's when, which we published in Scientific American, just like RSA. and that's when interest in quantum crypto really started.
It's really interesting. And I think the crossover between the cryptography and the physics
Yes.
is a difficult area because you can't really find reviewers at that time because it's such a new area. And
Right.
You obviously made it work because you had the background in cryptography and you were speaking with people who understood the physics. It's really quite an amazing collaboration.
Well, it's very true that quantum cryptography was the brainchild of the meeting of physics and computer science.
Mm.
We both expertises were needed. I would not have invented without Charlie, and I believe the other way around as well. So really, it was the meeting of two, at the time, completely distinct disciplines.
Yeah.
Because at the time, there was no connection between physics and computer science, essentially. Well, maybe one exception was that Bennett had already proven that reversible computing could be done universally. That was in 1971, I think, so really a long time before meeting me. That Bennett realized something that really is at a crossroads between computer science and physics.
Yeah.
But it's one of the very, very few exceptions before our work started.
So how does quantum key distribution actually work, and how do you think it will be applied at scale in practice?
Uh-huh. Well, the way it works uh, is actually very simple. Uh, I can explain it in a few minutes to someone who has no background in quantum physics. All you need to know is somewhat what I said before, which is that it's possible, in principle, with arbitrary accuracy and practice pretty well, to distinguish between the vertically and horizontally polarized photon, or between two diagonal photons. So you can distinguish between these two and between these two with arbitrary precision. But that no apparatus allowed by the laws of physics could distinguish between the four. So if you have a photon, you're told it's one of these two or one of those two, but so there are four possibilities, and you're not told which, then it's impossible. In principle, that's not a matter of technology, impossible in principle to tell them to say which of the four it is. So that's all you need to know. And then about physics. And then the protocol goes as follows. The original BBD4 goes as follows. Alice and Bob have no secret in common again. The idea is that we start with an empty slate. And Alice wants to establish, Alice and Bob are our two protagonists. And Alice wants to establish a secret key with Bob. So what she does, for some reason, is she will choose at random two bit strings of some length. The first bit string will be 0, 1, as a normal bit 0, 1 of message, that a message would have key. The second bit string will say whether these classical bits, 0 and 1 of the first bit string, whether they would be encoded rectilinearly or diagonally, much like what I said before. And then Alice would take each pair of bits, so again, 2-bit strings. Alice has one bit, which is a data bit, and one, we'll call it the basis bit. That will define one of the four possible photon polarizations. Alice sends that photon to Bob. So Alice will send as many photons to Bob. Each of these photons is randomly polarized in one of the four possibilities. But each one really means 0 or 1 if you know in which basis to read it. And Bob does not know, as opposed to the first idea we had before that was rejected. Now, Bob does not have knowledge of which bases Alice had used. So Bob chooses at random. Bob will choose at random for each photon he receives to distinguish it by measuring horizontal versus vertical, or plus versus minus 45 degrees. For each photon received, Bob chooses at random which measurement to make, independently of how it was encoded by Alice. And half the time, Bob makes the right choice. So half the time, Bob, if everything is perfect, now we have to deal with imperfections and eavesdropping later. But if everything is perfect, then half the time, Bob will make the correct measurement, the measurement that recovers the bit that Alice had encoded in that photon. And half the time, he makes the wrong measurement and gets a random bit that's uncorrelated with Alice's bit. So at this point, Alice has a bit string, the data bit string, and Bob has one that corresponds to what he received, measured. And about 3/4 of these bits are the same. One half are the same because Bob made the correct measurement, and the other half is the same because Bob chose the wrong measurement, but then he gets a random answer, which has a half chance of being correct. So now Alice and Bob's bit strings are 3/4 correct, but that's not good enough because he cannot tell which is good and which is bad. At that point, the quantum part is finished. And now Alice and Bob will discuss publicly, classically, the situation. Bob will tell Alice over a classical channel, Bob will tell Alice which basis he used for measurement of each of the photons sent by Alice, including, in fact, for each photon sent by Alice, Bob will say, oh, I chose to measure rectilinearly, or I chose to measure diagonally, or I just did not receive it. Because in real life, most photons will not be received. And then Alice tells Bob for all the photons that Bob has received, Alice tells Bob when were the correct measurements made, which was it the correct or the incorrect guess as what to measure. And then Alice and Bob only keep the bits corresponding to the correct measurement. And again, if everything is perfect in terms of the apparatus, except perhaps loss on the channel, and if there's no eavesdropping, then Alice and Bob's bit strings, what is left is the same for Alice and Bob. And that's the idea. Now, if there is eavesdropping, that will create errors. Eavesdropping, any attempt at eavesdropping will create errors, so that even though Alice and Bob should have the same bit string at the end, they will not. So after this process, they have to undergo a verification process. They have to do a process by which they will estimate the number of errors. That's easy. You just sacrifice some portion of the bits, and Alice tells Bob at random, chooses some proportion of the bits. Alice tells Bob, all right, this bit, this is what I sent. And Bob says yes or no, that's what I received. So they can estimate error rate. Once they have an error rate, from the error rate, they can estimate how much eavesdropping might have occurred. And now they have to reconcile the string. They have to make the strings shorter. They have to use error correction to make the string shorter but equal with very high probability. There's always an exponentially small probability that it fails. So in the process, they will do error correction, classical error correction, to reconcile their strings. So at the end, Alice and Bob have the same bit string. Now it's shorter, still shorter, but now it's the same bit string for Alice and Bob. And now Alice and Bob will know that the eavesdropper could have information about it, because it's possible that the eavesdropping gave some information. Eavesdropping on a quantum channel gave some information. And the process by which they do error correction also gave information. So now Alice and Bob know that the eavesdropper might have information about their near secret, and they can estimate how much information from the error rate. They don't know where it is, the information, but they can estimate how much information. And then they use a last classical process which we invented called privacy amplification, by which they can make their string even shorter again. But now, except with exponential small probability, if the upper bound they had on the amount of eavesdroppers information before privacy amplification, if this upper bound is correct, if indeed the eavesdropper had no more than that amount of information, even though he had no idea where is the information, then after privacy amplification, except with exponentially small probability, the eavesdropper has no information. So that's the whole protocol. And the way I explained it, there is one major defect, which is that there's an attack that this process does not take into account, which is known as the man-in-the-middle attack. I presented the protocol claiming that Alice and Bob had no secret in common initially whatsoever. In the extreme case, they've never met. They have no. They want to, for some reason, they want to communicate, but they don't know who the other is at all. Then, if an eavesdropper goes in the middle of the channel and does the entire protocol with Alice claiming to be Bob, and the entire protocol with Bob claiming she's Alice, then at the end, Alice will share a secret key with the eavesdropper, and Bob also will share a secret key with the eavesdropper. And that's not what we want. So we need a way for Alice and Bob to be sure that the message they receive in the classical, I forgot to mention that this classical communication has no protection against eavesdropping. That's done in the open. If the eavesdropper listens to the entire classical conversation that followed the quantum transmission, yet in the end, the eavesdropper does not know the key. So there's no protection against eavesdropping on that channel, but we must have protection against impersonation. It has to be what we call authenticated. So we need to add to this what I explained, to add protection by which when Alice and Bob have this discussion, this public discussion at the end, that Alice will know that what she receives from Bob came from Bob and has not been changed in transit, and vice versa. So that's what we call a authenticated public channel, the classical channel. So how can we implement authentication? And that's where the miracle happens. The miracle is that whereas Shannon proved that to get perfect secrecy, you need a key as long as the message you want to transmit. So the one-time pad is optimal. You can get perfect authentication. And when I say perfect, I mean protected by information theory, not computational. You can get perfect authentication with keys, secret keys, much shorter than the message you want to transmit. So that at the end of the day, if Alice and Bob share initially a short secret key, which they use for authentication, and then at the end of the process of quantum key of BB84, at the end of the process, they will get a much, much longer secret key, some of which they can keep for authentication next time around. And the rest they can use for privacy, for transmit a message. So in the end, what BB84 gives us, which is a way to stretch a secret key. You have a secret key of some length, but you need to bootstrap it for authentication purposes. Although there might be other ways to authenticate. But if we use this way to authenticate, then we need a short secret key initially. And at the end of the process, Alice and Bob have a much longer secret key. So what we get is a secret key expansion, which is protected by information theory and quantum theory, in the sense that if the initial key was perfectly secret, then the final key is perfectly secret. And this is provably impossible in the classical world. That's what, you have to make it, you have to work a bit on top of it, but essentially that's what Shannon proved in 1949. So it's classically impossible to stretch a secret key and keep unconditional secrecy on the longer secret key. And that's exactly what BB84 can do.
Excellent. And what's teleporting an unknown quantum state?
If you allow me, your earlier question was also about real life. So I just want to say that what I explained to you so far are the ideas that Charlie Bennett and I had in the 1980s, 1990s. I also mentioned that we built the first prototype in 1989. But this took off afterwards in real life because Charlie and I, we were held by 3 students for this initial prototype in 1989, but none of us were experimentalists. All 5 of us were theoreticians. And so we built this prototype, worked out over 30 centimeters. Not meant to be practical at all, just a proof of concept. But after that, some experimentalists got interested, in particular Nicolas Gilles in Geneva, but also John Rarity and Tapster in the UK, and also Richard Hughes in the US. So some people became interested in a challenge of implementing BB84 or other quantum cryptographic schemes over longer distances. And over the years, it became possible to do it over longer and longer distances. Today, to establish a secret key over 100 kilometers of optical fiber is a routine. The record, I think, has been like 1,000 kilometers of fiber, but that's with a very slow rate. And it's also possible, it's also been done to establish a secret key using a satellite. The Chinese did that. Well, when you stumble on one of my prizes earlier, this Chinese satellite is called Mencius, who was a Chinese philosopher more than 2,000 years ago. So Mencius sort of like Democritus made the idea that nature came in was not infinitely divisible. What Democritus called the atom. Messius had a similar idea. In any case, uh, the Chinese, when they built this first quantum satellite, they called it Messius. And then there was the Messius Foundation and the Messius Quantum Prize and all that. So they did this. It was launched in 2016, I believe, 10 years ago, almost. And it was used in one of the missions of the Messius satellite was to establish a secret key with BB-84 or variant of BB-84 between the satellite and Earth station and several Earth stations. And so they were able to establish a secret key between the satellite and Beijing. And then the satellite moved on. And they established a secret key between the satellite and Vienna. And the two keys were combined into a secret key between Beijing and Vienna, known only to the two parties and the satellite. And that key was used to encrypt the first ever video call over a very long distance, 7,600 kilometers, between the presidents of the Academy of Sciences of Austria, who was Anton Zeilinger at the time, and China. So all that to say that these ideas that were purely theoretical, but that Charlie and I invented at the time, they've become practical. In China, there is a 10,000 kilometer backbone of optical fiber across the country. Of course, 10,000 kilometers is not so big for China, but still, that in particular that links Beijing to Shanghai. So the Chinese are using quantum cryptography in real life. Europe has important initiatives to do that. Something that was called OpenQKD as a quantum key distribution, which was somewhat replaced by EuroQCI as a quantum communication infrastructure. So both OpenQKD and EuroQCI are initiatives to build a quantum cryptographic network that will link all of Europe. I must say with some sadness that whereas quantum QCI, was EuroQCI, the new thing, has partners in every single country of the European Union, and therefore, with sadness, not Switzerland nor the UK. But except for that, it's doing great.
Yeah,
Sorry for you.
this is a shame. I think the UK is getting much closer to the EU research again. So hopefully that
I know you're doing
yeah,
your best. The Royal Society is helping.
yeah,
So it's a big disaster.
yeah,
Brexit was a disaster for science,
yeah,
of course, but not only
yeah,
for science. Anyways, just to finish the story. So the short story is that quantum BB-84 and quantum cryptography in general is now being deployed on a massive scale in China and Europe, much less so in America, and also in Japan and in South Korea. It's a big player as well. So it's a real thing. It's a real thing. Isn't it? When we invented that back in more than 40 years ago, we never thought that it would become serious. We were just having fun. And it's a total surprise for us that it's become so big.
yeah. So what's teleporting an unknown quantum state?
Well, as I said before, quantum information, one of its properties is that it cannot be measured reliably, cannot be copied. Any attempt at measuring it will give incomplete information and disturb it. So what if Alice, say again her, if Alice has a quantum system, it's in some quantum state that's unknown to her, and she would like that quantum state to instead be in possession of her friend Bob. Well, she could physically send the quantum system to Bob, of course. That would be no fun. She could do it, but perhaps along the way, it might get lost. Or to do that, she needs to know where Bob is. The idea of quantum teleportation is that it is possible for Alice to transmit this information to Bob by sending a classical message. And this sounds totally impossible because she cannot measure it. If she could measure the information, well, first it would be an infinite amount of information. If it's a polarized photon, it could be any angles. If you want to transmit exactly, you need infinite number of bits. But you cannot even measure it anyway, so forget it. So how could Alice possibly transmit a quantum information to Bob by a classical signal, since she cannot measure it? Well, quantum teleportation is the answer, but it requires Alice and Bob initially to share what we call entanglement. And entanglement is the most amazing aspect of quantum information. I won't get into detail, but when two particles are entangled, this was discovered by Einstein, Podolsky, and Rosen in 1935, and recognized by Schrödinger as the most fundamental aspect of the quantum world. So if two particles are entangled, then it appears, and I insist on appears. It appears as if there is a instantaneous channel that links the two of them, so that if you do something to one of them, the state of the other particle will change instantaneously. This is what Einstein called spooky action at a distance, which he totally dismissed with a reason. But I come back on entanglement at the end. But back to teleportation. If Alice and Bob have access to this entanglement, again, meaning that they have established entanglement already between them. And if Alice wants to send a quantum state from Alice has a particle that's entangled with one of Bob's, arbitrarily far away. And now Alice wants to send a quantum state of a particle that she has. What she will do is she will do an operation that involves both the particles she wants to teleport and her share of the entanglement. She will do something here whose effect will be to destroy the information she has. So she will lose the quantum state she wanted to teleport. But it appears as if that's not what happens. But it's as if instantaneously at Bob, who I remind you, Bob had a particle that was entangled with Alice initially. So on Bob's side, it appears as if the particle that Alice wanted to teleport, the state of that particle will appear in Bob's particle. But very strangely enough, in a way that is encrypted by nature. So nature will encrypt the information that Alice wants to send to Bob in a way that is unconditionally secure from a cryptographic point of view, unless Bob has the decryption key. And it turns out that the decryption key is given to Alice. So again, when Alice did her operation here on her share of the entanglement and the particle to teleport, when she did this operation, she obtained classical information as a result, because that's a measurement. What she does is in fact a measurement. And that gives her classical information. And that classical information obtained by Alice is exactly the decryption key that Bob needs to transform his previously entangled particle into an exact copy of what Alice wanted to teleport. So now Alice has to send this classical information over to Bob classically, over a classical channel. And when Bob gets the information, then he can decrypt the particle and get an exact copy of the original. So this does not contradict the no-cloning theorem of quantum theory, because Alice's state, the particle at Alice's state, is gone. So Alice loses what she wants to teleport. So you win that from one copy make two. Alice doesn't have it anymore. Only Bob has it. So no cloning is not violated. And it does not violate Einstein's special relativity, because the teleportation is not finalized. What Alice wants to teleport does not appear at Bob's until he deciphers it. And for that, he needs to wait for the classical information from Alice. And that does not go faster than light. So the teleportation process appears to have one first phase that is totally magical and instantaneous, and a second phase, which we call the correction, which has to wait at the speed of light for the information. So at the end, teleportation does not occur faster than the speed of light and does not allow to copy a quantum state. So it does not violate neither quantum theory nor special relativity. And so I said appears to, and of course, I guess you want to know what really happens, and I'm not going to answer it.
Yeah. Okay, so you've won so many awards. Which one are you most proud of?
Well, the most, I would say, intense moment in my entire professional life was to sign the Royal Society Charter Book.
Mm-hmm.
So when I was elected as a fellow at the Royal Society of London, I had the occasion to sign a book dating back from 1660. Literally, it's the same book. It's not a. It's the original pages are still there. Well, it's a new binding, yes, okay, but the paper is still the original 1660 pages, and I was signing this book, knowing that Newton had signed it before me.
Wow.
And Darwin. Well, Einstein never came to sign it when he was elected as a foreign member, but Newton and Darwin had signed the same book centuries before me, and signing that book is the most amazing moment in my professional life.
Yeah. I must agree. I'm a fellow of the Royal Society of Edinburgh. I appreciate it's not at the same level, but James Clerk Maxwell, who has a statue just across from the Royal Society in Edinburgh, actually was a fellow too and signed the book. So I must.
Oh, I understand. Yes, of course. You being a fellow of the Royal Society of Edinburgh.
Yeah.
Yes. Well, I'm pretty sure that they also signed the Charter Book of the Royal Society of London. So I mean, surely they were fellows of both societies. So.
They were, yeah. I think he did most of his work in Cambridge, so he would have been part of the Royal Society of London too. So I completely agree with you. It's an amazing thing to be recognised.
There's nothing like it.
Yeah,
and I'm glad that you also had this occasion.
Yeah. And so my final question is really to ask you what you're currently working on. I know that you're semi-retired, but you kind of stop your brain from working.
Well, I work mostly at the moment on the foundations of quantum theory. So I would say that my first, in the first part of my professional life, after meeting Charlie Bennett at least, my main interest was how can I use this knowledge now I have? How can, let me try again. How can quantum information, I try again. Sorry. Let me start. How can I use quantum theory to make better things in the world of computer science? How can quantum theory help computer science do things or achieve things that would not be possible in the classical world. For instance, perfect cryptography. For instance, factoring very quickly. And that's all very exciting. And there are so many other things that we didn't have time to discuss. Let me just mention one, which is communication complexity. We didn't talk about it, but I think that's really interesting. So you have two, could be more, so two people, they each have a private input, and they want to compute some function of both inputs, of both inputs together. And it's not a question of cryptography. They're not trying to hide their input to the other, but they want to compute, let's say, Alice has X and Bob has Y. They want to compute f of xy. And what they want to do is to have as little, to minimize the amount of communication between them. Well, this is a field known as communication complexity. And it's known that if Alice and Bob are entangled, if they share prior entanglement, then there are some things that they could compute with exponentially less communication between them. And I find that very interesting. And there are even tasks, not computing a function anymore, but giving an output. So they get an input, they have to give an output. Each one of them has an input that needs to give an output. And they have to do that in a way that the pair of outputs respects some restriction from a pair of inputs. And there are some problems for which they can do that perfectly with entanglement without any communication. Whereas if they were purely classical, they would not be able to win this game all the time without communication. That's what we call pseudo-telepathy. It looks like Alice and Bob have telepathic powers. Of course, they don't, but we call that pseudo-telepathy. And that's something that entanglement makes possible. And I'm currently working with my students on problems in which, in multi-party scenarios, in which you have this pseudo-telepathic phenomenon that occurs between the three parties in this case, or maybe more than three, but they need tripartite entanglement. And if they had bipartite correlations, they could not do it. Anyway, I'm maybe too precise. So that's the type of thing I'm working on at the moment. But back to what I was saying before. For a long time, I was interested in what quantum theory can do that is interesting for computer science. And this is an example. What I just said, so telepathy is an example. But then I realized that a much more interesting question was, what can computer science do for quantum theory? And how can I use my computer science background to understand quantum theory in a different way than a straight physicist would do? And in particular, back to entanglement. Entanglement, as I said before, gives the impression that there's this instantaneous communication. Give this impression known as non-locality. The standard way to describe entanglement is that when I do something here, if you have, as I said before, I have two entangled particles, and when I do something here, it has an instantaneous effect that changes the state at the other side. Standard quantum theory tells us that it seems like this is what happens, even though what the change at the other side cannot be measured. So that does not allow to communicate. Good. But still, there seems to be an instantaneous change of the state that occurs instantaneously. Again, what Einstein called spooky action at distance. So, and the question was, can this be explained? Can we explain what quantum theory predicts as a result of experiments by a theory that would not require non-locality. In other words, what Einstein wanted. And the answer is yes. Even though it seemed that the answer would be no. Because, again, entanglement was discovered in 1935. And we had to wait till 1964 before John Bell realized that whether these things are real or not could give rise to an experimental verification. Something that we call Bell inequality. That in any theory in which information would be, in any theory that would be ruled by what we call local hidden variables. So with local hidden variables, John Bell proved that some experiment could be done and the outcome would not be bigger than 2, whatever that means. But quantum theory predicted 2 root 2, 2 times square root of 2, which is bigger. 1964, still theory. In 1972, John Clauser made the experiment for the first time. And indeed, he was able, what we call violate the Bell inequality. He did an experiment in which he did something that's somewhat like what Bell had proposed. And he got a result bigger than 2. So this ruled out what we call a local hidden variable explanation for quantum theory. And then Alain Aspect, 10 years later, did a much more convincing experiment. And they got a Nobel Prize with Anton Zeilinger in 2022, 50 years after Clauser's experiment. So at that point, it seemed very clear that the experiments had vindicated quantum theory. And therefore, because of Bell's theorem, we could not explain quantum theory in a way that could explain our universe with local hidden variables, which I did not explain what it is. And it seemed to mean that our universe is non-local. In other words, that these instantaneous action at distance take place. And some people really believe that. In particular, Alain Aspect is convinced that this is really what's going on. Alain Aspect really believes, again, Nobel Prize 2022, really believes that if 2 particles are entangled, by doing an operation here, you can actually change the state of that one instantaneously. He believes that. And I don't. I side with Einstein, which is that all this can be explained without resorting to non-locality. The short story being that what has been proved is that you cannot do it with local hidden variables. And I'm really sorry I didn't explain what it is. But local hidden variables is not the only way to be local realistic. Einstein wanted a local realistic theory of the universe. And he believed it could be achieved, but didn't manage to do it. But now we know how to do it. In fact, this was discovered initially by David Deutsch. The same David Deutsch was the father of quantum computing. And Patrick Hayden. So Deutsch and Hayden in 1999 found a way to explain all these apparently non-local correlations that quantum theory predicts. Give an explanation that is totally local and realistic all the way through. But that paper did not get much attention. Later, one of my students, Paul Raymond Robichaud, not knowing of the Deutsch Hayden ideas, discovered that it's possible to have a world that is local realistic and violates Bell's inequality even more than quantum theory. thus establishing that a violation of Bell's inequality as such is no proof of non-locality. And then he was able to derive a complete explanation of quantum theory, which is somewhat equivalent to Deutsch-Hayden. So the short story is that we can explain everything that quantum theory predicts in a universe that is purely local and realistic, in which there is no action distance whatsoever. And all these people who believe that they have proven that our world is non-local by doing experiments that agree with quantum theory, well, they're wrong. When they have a Nobel Prize, good for them. But they're wrong in the sense that if they really wanted to prove that our world is non-local, if that's really what they want to do, then they have to find an experiment that will disagree with quantum theory. Because, as I said, everything that quantum theory predicts can be explained local realistically. So the only way to be non-local is to not agree with quantum theory. And that could happen. But that's not what these people do. These people are very proud, rightly so, very proud of again and again vindicating quantum theory by more and more elaborate experiments. But again, none of these experiments will prove our world is non-local. And I'm not saying that the world is local. I'm saying we don't know. I'm saying there is no evidence whatsoever that it's not local. And now it's philosophy, not physics. It's philosophy. But remember that philosophy was the first of all sciences in old Greece. And that we get a PhD where PhD means philosophy. So philosophy is a great, great thing, even if it's not hard science. So it's philosophy, but I like to believe, if I have a choice, if I can tell God what to do, I have a choice in which our world would be local, realistic, and no experiment that has been proposed or done so far proves the contrary. So maybe we'll never know, but that's how it is.
Well, it's been a real privilege to speak to you. The way that you've fused two areas together, your cryptography and physics, is just wonderful. You've created a whole new world, and now the next 2 decades are going to be such a wonderful time of change. And I think you've laid the foundation for others to build on. So thank you so much for that.
Oh yes, there is still a lot of work to do.
Yeah. Okay.
This is not the end of the story. It's only the beginning.
No, that's right. Yeah.
Thank you
Thank
very
you.
much, Bob.
So thank you so much.
Thank you, Bill. It was a
Thank
pleasure
you.
talking to you.